This conference will now be recorded.
Hello everyone, we have finished the nomenclature part. So based on that, we'll discuss 2 to 3 problems, and after that we'll start isomerism. So today it will be discussion related to isomerism only. Here we have a problem, and that is based on aromatic compound nomenclature. Fine. So in this compound, we have to find the IUPAC name. 4 names are given in the options. Now look at the groups. Here we have CONH2 group and we have Cl. Now among these two groups, these groups gets preference over Cl. Okay. Now we have seen that for Cl, when it is used as a substituent, the name that we are going to use is cyano. Similarly, for the group CONH2, normally, if it is only present in the benzene ring, like benzene ring and then CONH2, this group is actually amide group. But when it is used as a substituent, the name will be used carboxamide. Carboxamide. So it is amide of the carboxylic acid. So suppose we have carboxylic acid like RCOOH, and then in place of OH, if you replace it with NH2, RCONH2, then we will call it amide. But when it is attached to this benzene ring like this, and as it is carboxylic acid derivative, so that is it is carboxamide, and its position is 1. So it should be having more priority compared to the other group, which is Cn. And in the name there must be the mention of the name benzene, because with the group we are not using any we are not changing the name benzene. What I am trying to say, suppose when OH group is attached to benzene ring, or suppose CO2H group is attached. So in these cases, or CHO group, so only in these 3 specific cases, mostly according to IUPAC, that is preferred, we use phenol, benzoic acid or benzaldehyde. So the term benzene is not mentioned in that case. But for other cases, except these 3 groups, that is not, we do not give preference to this because that is not preferred according to IUPAC. So that is why these 3 groups are not present. So these 2 groups we will consider it as if it is substituent. And here position 1, that will be starting from this position where CONH2 group is present. So you will move to this direction, not move towards either another direction, because if you do so, then the numbering will be like this: 2, 3, 4, and cyano will get 5. But 1, 3 is obviously better than 1, 5, so that is why we will focus on 1, 3. Now look at the options. Here in the option A, it is mentioned as carbamoyl, but this type of term is not used. And also cyano will be used, not nitrile. Here it is mentioned, that is CN group is mentioned as carbonitrile, but that is not the right way to use this. That is, this term is not right. Then in option C, we have alkane nitrile and alkyne amines. But 2 separate names obviously will not be there. There will be a single name. And then we have B and D. In D, it is 3 aminocarbonyl cyanobenzene. That means position 1 is given to that carbon where CN is present, but that is not right. So that is why only option B is left, which will be correct option. 3 cyanobenzene, 1 carboxamide. Next problem. IUPAC name, again a structure is mentioned. Now as there is CO2H group, so we have to consider it is as a derivative of benzoic acid. So it will end with oic acid, and as benzene is present, so that is why benzoic acid. Now benzoic acid, it is that is ending with benzoic acid, that you can find in option 2, option 3 and option 4. So option 1 will not be correct. Now this is number 1, that is fine. But whether you will move to CN first or CHO first. So which one is correct? Is it that number 2 is cyano, and then if we do so, 2, 3, 4, 5, 6. Then 6th position it is CHO. And another probability is the reverse one, that is 2 CHO and 6th position cyano. But what we have to do? just write the name without any number. So cyano and CHO. For CHO, when it is not the main group, it is having less priority compared to CO2H. So CO2H is the mother group here. And CHO, now the term we will use for it is formyl. Now formyl F, and here it is cyano. So cyano we will write first, then it will be formyl. Now here also it is 2,6, and if you do the reverse one, then also it is 2,6. But which one we will choose? We will choose this one, because we have to give priority to CNO as it is present before formyl because of alphabetical order. So 2 cyano, 6 formyl, and after that it will be benzoic acid. So 2 cyano, 6 formyl, benzoic acid, not the other option. That is 2 formyl, 6 cyano. See, that is present in this case, but F you cannot write before cyano. So cyano you have to write first, and then put 2 before this. So this is the correct option, option 2. Here again we have a molecule. I can also write the molecule so that it helps to understand. CH3, CH3, then CH. Here we have pH. C6H5 is pH, that is benzene ring is attached. Fine. Now here NH2 group is present. Now except pH, if you look at the rest of the part, here total number of carbon is 1, 2, 3, 4, total 4. And in benzene there is total 6 carbon. So according to that pH should be given priority. But see, as NH2 group is present as functional group, so it must be that pH is treated as substituent, though here number of carbon is lesser than 6. Still, because of presence of NH2, pH will be treated as substituent. Now if pH is treated as substituent, numbering will be started from this carbon, then number 2 carbon, this is number 3, and this is as if substituent. So we have substituent at 1 position where pH group is present, and we have methyl substituent at 2 position. Fine. Now among methyl and phenyl, M comes before P, so that is why you have to write methyl first and then phenyl, whatever is the position. So 2 and then 1. So 2 methyl, 1 phenyl, and total number of carbon in the parent chain is 3. 1, 2, 3. So that is why it should be propan. And after propan it should be ending with amine, and the position of amine is 1. Okay, so that is why this should be the correct option. And whenever you are writing propan, this E will not be there, it will be omitted, because amine is starting with vowel. That is the rule. So that is why 2 methyl, 1 phenyl, propan, 1 amine. And why the other options are not correct? Look at the other options. Suppose option A, what is the problem? Here it is mentioned 1 amino, 1 phenyl. That means amino group is also treated as substituent, but that is not correct. Only 2 substituents are there, phenyl and methyl. And also phenyl is written before methyl. That is also not right. This is not correct. Then option C, 2 methyl, 1 amino. Again, it is treated as substituent. And option D, see here the parent chain, 1 isopropyl, 1 phenyl, methyl. It is actually completely wrong, because isopropyl is not the substituent. If you choose the longest parent chain, there is total 3 carbon. So only substituent left is methyl. Isopropyl is not the substituent. Isopropyl is basically this group, CH, Me2. This is isopropyl group. But here this type of substituent is not present. Now there is no question, but for this molecule we will try to write the IUPAC name. So here we have phenyl ring, right? And we also have some carbon hydrogen chain. Now see what is the number of carbon except phenyl, number 1, 2, 3, 4, 5. So it is less than 6, but still we have to give priority to this carbon hydrogen chain. Why I am saying so? Because of presence of this OH group. So numbering will be starting from this carbon, because we have to choose the longest chain. 1, 2, 3, 4 and 5. So at one position there is no substituent, sorry. 2 position we have phenyl, and OH is the main substituent, so it will end with all. But 2 position there is PH, and at 4 position there is in, and the name should be ending with all. So it should be 2 phenyl, pent 4 in, 2 all. So 2 phenyl, this is the substituent, this is treated as substituent. Then pent, because in the longest parent chain we have total 5 carbon. Then at 4 position we have double bond, so that is it is 4 in. And at 2 position we have this OH group, so that is why it is ending with 2 all. Okay, so this is the correct IUPAC name. So these are some of the examples, that is in this slide the 2 examples that we have discussed. These are some such examples where you have to choose whether you will give priority to the benzene ring or you will be treating the benzene ring as substituent. So in both these examples, we have treated benzene ring as substituent, and NH2 and OH groups are given priority as functional group. Now we will start isomerism. Now, what is isomerism? Isomerism represents the existence of 2 or more compounds with same molecular formula. So at least 2 compounds must be there if we want to use the term isomerism. And these 2 compounds, they are actually isomer to each other. Okay, so they must have same molecular formula. That means, suppose if you consider, obviously organic compound we will consider. If we have same number of carbon, hydrogen, and if any heteroatom is present, and suppose another molecule is also having the same number of carbon, hydrogen, and heteroatom if present, but they are having different structure, different physical chemical properties, then this relationship between them, if it is 2 compounds, it is okay, at least 2 compounds must be there. It may be more than 2. So suppose there are total 4 compounds, all are isomers to each other, that is also possible, but at least 2 compounds must be there. So very simple example we can take. Suppose we have ether, CH3OCH3, and we have CH3CH2OH. The second one is alcohol. Now in the first case, total number of carbon is 2, hydrogen is 6, and oxygen. So this is the molecular formula. And in the second case also it is C2H6, 3, 2H, and 1 oxygen. So see, both cases molecular formula is same number of carbon, hydrogen, oxygen, but structure is completely different. And in the second case we have OH group, in the first case we have ether. So obviously physical, chemical property, everything will be different. So these 2 compounds, they are isomer to each other. Now there is different types of isomerism possible depending on what is the relationship between them. So we will see a flow chart which will show us the different possible isomerism that are we see in organic compounds. Now the difference in properties of 2 isomers, it is because of difference in the arrangement of atoms within their molecule. So here bond connectivity is completely different. Why I am saying bond connectivity? See, here oxygen is between 2 carbon, but that is not the case for the alcohol. Here oxygen is between carbon and hydrogen. So here properties will be different. So bonding connectivity is different. Same type of bonds are not present. Another term you are also seeing here, though right now you will not be able to understand it. To understand it, you need actual examples, and we will discuss later. So spatial arrangement, that means 3-dimensional arrangement. So if we want to understand spatial arrangement difference between 2 molecules, obviously you have to imagine the molecules 3-dimensionally, because the difference is in spatial arrangement. There is no difference in bonding connectivity. That is another type of, that is a special kind of isomerism, stereoisomerism. where bonding connectivity is same. That is same type of carbon-oxygen bond or OH bond. Everything is same, but how they are arranged in three-dimensional space, that arrangement is not same. So sometimes it may be difference in bond connectivity, as you are seeing in these two examples, but sometimes it may be spatial arrangement also. So these, based on these, we have this flowchart that we are going to see. So the first category that we have here, structural and stereo. So stereo, obviously, as you I have just said, that it is because of the change in spatial arrangement, there is no difference in bonding connectivity. But when there is difference in bonding connectivity itself, that is same type of bonds you will not find. Different groups, different bonding connection. So that is treated under structure. Okay. Now the structural, sometimes this is for this same category, another term is used. Maybe in some other books you will find different term. Don't think these two are different. These two are actually same. So structural, the isomers, they are also called as constitutional isomers. Same formula, different connectivity. Same thing. Now under structural also we have so many variety, as you are seeing here: chain, position, functional, metabolism. So one by one we will cover all of them with proper examples. Once we finish this part, then we will move to stereo. And under stereo also you can see there is different categories. First there is configurational and conformational. Then under configurational we have further categories. Okay. So we will start with structural isomers or constitutional isomers. So structure or constitutional isomers, what it means, compounds having same molecular formula. Now if I do not say it, then also obviously it is the basis of isomers. If two compounds, they are not having same molecular formula, no question of isomerism exists. Okay, so they must have same molecular formula. It goes without saying. But differ in the manner of linkages between atoms within the molecules. That means different bonding connectivity when present. Then this phenomena is called structural isomerism, and the compounds they will be called isomer to each other. The first type under structural or constitutional is chain isomerism. Now for chain also sometimes different terms are used. So I have mentioned all the terms so that if you are getting any different terms mentioned in the question, you will not be you will be able to understand which it actually means. So instead of, mostly it will be mentioned as chain, but suppose instead of chain it is mentioned as skeletal isomerism, that also actually chain isomerism, nothing different. And here difference is in the arrangement of carbon chains. So main focus should be on the carbon skeleton. Okay. And this type of isomerism, it is mostly you will find in case of alkanes. I am not saying it is not possible in other cases, but mostly you will find it in case of alkane. Because whenever it is not alkane, suppose if I am saying it is alkene, then there is CC double bond, then there is CC triple bond. So what happens, as these are also treated as groups, so some other types of structural isomerism may arise. That means when these double or triple bonds are present, there are some other types that we'll also discuss in today's class only. Then that probability also arises. But when it is alkane, mainly you will see most of the examples under chain isomerism, it is for alkane, though it is possible with others also. So here we will see this example. All these 5 molecules that you are seeing, they are actually having same formula. Now what is the formula? Here total number of carbon is always 6. Whether you consider any of this molecule, it is always total number of carbon is 6. And as it is alkane, if you just focus on the first, we know the formula is CnH2n plus 2. That means 6 into 2, 12, and then 14. You can also count it here, total 3 hydrogen, then 2, 2, 2, 2, that means 4 into 2, 8, 3, 3, that means 14 hydrogen. Now, if it is asked, suppose it is mentioned in the question, write all the chain isomers that is possible with the formula C6H14. Then you have to draw all these molecules. Now, how you will start? The simple way to start it, as suppose forget about the picture. Suppose only the formula is given and it is mentioned that you have to draw the molecules. Then what you will do? How you will start? You will start from hexane, because as it is 6 carbon, the simple molecule that you can draw is hexane. Now once you have drawn hexane, next move to pentane. Here parent chain there is total 5 carbon, and when it is 5 carbon, this extra carbon you have to place as substituent. Now substituent position you can place it, if I am numbering 1, 2, 3, 4, 5. The substituent you can place either at 4 or 2. Both are actually producing same molecule. It doesn't matter anything. So next possibility is if you place the methyl substituent at the middle carbon, that means at 3 carbon, then you will get 3 methyl pentane. Now under pentane you can have maximum these two. Then go to 4 carbon, that means under butane what you can have. So when it is 4 carbon parent chain, now what will happen? You will have now 2 methyl substituents. So these 2 methyl substituents, now they are at position 2 and 3, but they can also be present at the same carbon, and that you are getting in the next picture. So it is 2,2-dimethyl butane, because this is the position 2. And if you are thinking why not 3 carbon chain, now see, when it is 3 carbon chain and if you are placing 2 methyl, suppose you are placing 2 methyl here. Okay. Suppose you are doing like this. So you will see basically it is again creating the same structure as if it is 2,3-dimethyl butane. So 3 carbon chain it is not possible. So these are the maximum possibilities already that you are seeing here. Under 6 we have only 1, under 5 we have 2, under 4 parent chain we have again 2. So total 5 structures possible as chain isomer for C6H14. Now suppose if I am saying do the same thing for with a CC double bond. Now for CC double bond, the formula that will be changed. Suppose now I am doing with C5, and for alkene the formula is CnH2n, so it is C5H10. Now under C5H10, the simple structure that you can draw first is this one, 1, 2, 3, 4, 5. So it is 1 pentene. Now the next possibility is, suppose if you are drawing the molecule, sorry, suppose you are drawing the molecule, again 5 carbon, now the position of double bond is like this. But these two should not be called chain, because the same chain is there. These two both are 5, only you have changed the position of the double bond. So it is not considered under chain. It will be considered under position isomerism, that we will discuss in the next slide. So this picture, the second one, that cannot be the correct one. Now which one may be correct? Suppose I am changing the parent chain itself. So instead of 5, now I am drawing 4 only. And then I am placing the double bond same position, and 1 methyl that will be at this position. Now you can say that the second molecule, that is chain isomer of the first one, because we have not disturbed the double bond, which as if group here, we have not disturbed that. We have just changed 1 carbon in the parent chain, it is now less, and that is treated as substituent which is present at this position. Okay, so this you can call as if chain isomer. But again, if you are keeping everything same but you are changing the double bond, now it is not under chain isomerism category, that will not be correct. But suppose you are drawing the molecule like this without disturbing double bond. Now the methyl is here as substituent. In this case, you can say it is a chain isomer of C5H10. But these structures under C5H10, that is possible only if it is mentioned clearly that only draw the chain isomerism of isomers of C5H10. Because if it is mentioned that draw all the structural isomer of C5H10, then there is so many other possibilities. That is not restricted only these three pictures. When it is mentioned as structural, because under structural there is so many variety that you have already seen in the flowchart. But if it is strictly mentioned only the chain isomers, then these are okay. And also it should be mentioned that it is not cyclic, because we have ignored the cyclic structures. Fine. So these are examples under chain, and that is mostly you will find for alkanes. That is the first example. Now position isomer. So in this case, what happened? The position of the multiple bond or functional group changes, but the basic parent chain that is not changed. So see example. Here we have OH group. Parent chain here butane 1 all, it is butane 2 all. That means here total number of carbon 4. This is also 4 carbon. We have not changed the basic chain. We have just changed the position of OH. In the first case, it is at the first carbon. Now it is at the second carbon. That is the only difference. So position is changed. Fine. Another example. Now this example contains multiple bond, no functional group. Paint 1I, paint 2I. So in the main chain, it is always 5 carbon, whether you consider the first molecule or second molecule. But here the position of triple bond is at 1. Here it is starting from 2. So position of the triple bond is different. Paint 1I and 2I. So these are the examples. One example with functional group, one example with multiple bond, since the triple bond. Now one more example also you can consider. Here we have benzene ring and 3 carbon chain at 2 position if you consider methyl at 1. But in the second molecule, position of methyl intact. Now this 3 carbon chain, it is changed. So you can consider it as if it is positional isomer. But look at the second molecule example. Here this part is fixed for both. This is 3 carbon chain, but the chain, this is also 3 carbon, but the chain design is not same. I mean to say the branching is not same. Here it is simply linear chain, but here we have isopropyl type of group. Okay, so you can say that their positions are different. In the first case it is 1, 2, it is in the second case it is 1, 3. But position isomer, that term only arises if rest of the part is same. That is chain is same similar type, but here chain is already different. So chain is different, so that is why we are calling it chain isomer. The third type is functional isomers. For the name, from the name you can itself understand. Now different functional group will be there. Remember one example I have shown before the showing the flow chart. One is ether, another one is ethyl alcohol. So that too actually example of functional isomer. Same molecular formula but different functional group. So see, this type of functional isomerism you will mostly find in case of same number of carbon containing ether molecule and alcohol. So this is ether, this is alcohol. The example that I have shown, that is also ether. This example I have shown, remember? Ethyl alcohol and dimethyl ether. Here though it is different. So these two are examples of functional isomerism, different functional groups. Next, here we have acid, carboxylic acid, and this is H star. So whenever you have same carbon, acid and H star, in acid also there is always 2 oxygen, H star also 2 oxygen. Number of carbon is also same, 1, 2, 3, 4. Here 3 carbon here and other side 1. But formula is same. The formula is total 4 carbon, 8 total number of hydrogen and O2. So C4H8O2, whether you consider this one or the ester molecule, formula is same. So ester and acid, these are the two class of compounds where you can find functional isomerism, that is common. Then we have ether alcohol, acid ester, and then we have aldehyde and ketone. So aldehyde and ketone, when they are having same number of carbon, because in both cases there is only one oxygen. So it is 4,8,O. Same molecular formula you can also find for the ketone. So it is aldehyde because on the right hand side you can see hydrogen, and it is aldehyde. So you must have hydrogen on one side of the carbonyl group, but here both side we have alkyl group. That is why it is ketone. So these are pair of class of compounds: ether alcohol, acid ester, aldehyde ketone, where functional isomerism you can find. The fourth structural isomerism is metamerism. Now this is something interesting. It cannot arise always. This type of isomerism arises only when there is a functional group which is bivalent. What I mean by bivalent? So any functional group where both sides there must be valency fulfilled. Suppose I am saying OH. So OH is such a functional group where only one side it is attached. But suppose if I am saying ether, both side it is attached, isn't it? Then if I am saying ketone, both side there is some substituents. Then ester, both side there is some substituents, right? It is also applicable for secondary amine. Secondary amine means R2NH. So secondary amine, there is two R groups attached both sides. So these are the groups where you can find metamerism, and this type also arises due to unequal number of carbon atoms on either side of functional group, or different alkyl groups attached to either side of functional group. So not that always different number of carbon. Sometimes it may be that both sides we have same number of carbon, but still the chain is different. The branching in the chain is different. Then also metamerism is possible. And this is shown by compounds having functional group ether, ketone, ester, secondary amine. That is bivalency must be there. So you cannot have it for OH. That is not possible. Metamerism is not possible. Because from the definition it is clear both sides there must be something. Now look at this example. So these three molecules, all of them are ether. Now number of carbon also if you see 6. So for all the formula is C6, then hydrogen 14 and oxygen. So whatever molecule you choose, it is always having the same formula. But see here total number of carbon is 1. In this side 5, 2, 3. Then we have, it is 2, 4. Then it is 3, 3. So obviously we have different number, unequal number of carbon. But sometimes it may be same number of carbon, but still there is some difference. For example, suppose this molecule, I'm keeping the same number of carbon. So I'm not disturbing the left hand side. See, I have not disturbed, same. But right hand side, instead of writing simple linear chain, if I am doing some branching like this is also 3 carbon. And this side I haven't changed anything. So 3, 3, this is also 3, 3. But still there is some branching. So the alkyl group is different. So whether it is unequal number of carbon or different alkyl group, in both cases you can consider it as if it is metamerism, right? Now we are seeing example only with the ether, because mostly it is you will find it in ether, but there is sometimes you can have some confusion. But see, the confusion arises because what happens in some molecules, metamerism can be overlapped with chain or position. So what I am trying to say, suppose I am drawing this ketone. So what you are seeing, this side we have 1 carbon, other side we have 2 carbon, right? Okay, let me draw one more, 3 carbon. Now the same molecule, suppose I am doing like this. Now it is 3 carbon. This is also 3 carbon. Sorry, it is 1 and 3. That means total number of carbon, because this is carbonyl carbon is fixed. 1 and 3 is 4. So if this side, one minute. Let me draw it clear. One, two, three, 4, 5. Okay. And then I have just changed the position of CO from 2. Now it is at 3. Right. Now in the previous slide, we have just finished the definition of position isomer. Remember, just have a look. So position isomerism means the isomers differ in the position of multiple bond or functional group. Now this functional group, suppose if it is carbonyl functional group like this. So this is also functional group and total number of carbon it is 5. Here it is at 2 position, but now in the second case I have shifted its position from 2 to 3. So these two molecules you can consider at position. Now when this position isomerism it overlaps with metamerism, it is possible in those cases where the functional group carbon itself is the part of the parent chain. Then only this type of problem arises. So see here at a first glance it seems as if it is position isomerism. But if I say it is also metamerism because of different number of carbon of the both side. That is, it is also fulfilling the criteria of metamerism definition as well as position isomerism definition. So that is why here it is 1 carbon, 3 carbon, and in this case it is 2 carbon, 2 carbon both sides, symmetrical structure. But whatever it is fulfilling the criteria of meta and position isomerism. So that is why these two are observed simultaneously. And this is possible only when the functional group carbon, functional group contains carbon. You cannot have this problem in ether because in ether there is no carbon attached to this functional group. But in case of carbonyl, it can be observed. This problem can arise. And sometimes metamerism can be observed with chain isomerism. That you can find in this example. See, if I say that this molecule and this molecule, these two are chain isomerism, then also I am not wrong. Because here if you look at the chain, there is difference in the chain because this methyl you can treat it as if substitute. So these two molecules they can be considered metamerism as well as they can be considered chain isomers. This is the problem. Okay. So sometimes these two are observed simultaneously. That is metamerism along with position or metamerism along with chain. The next one that is type, which is fifth type, and this is tautomerism. Now tautomerism, here you will have to that is complete bond. Here also bonding connectivity is different, but these two are interconvertible. They can change to each other, which you will not find in other types. That is until now, whatever types we have discussed, this is something new we are seeing, that a single compound, it can exist in two readily interconvertible structures. And they are in dynamic equilibrium. Now they differ in the relative position of at least one atomic nucleus, and mostly this atomic nucleus is hydrogen. And their relationship is tautomers, so they remain in pair, and there is dynamic equilibrium. Now the most common tautomerism observed in keto compound. So in keto compound, here we have taken acetone, which is the simplest ketone compound possible. If I am drawing the structure elaborately, it is 8-methyl, then CO, then CH3. Now instead of writing CH3, suppose one hydrogen, if I write like this. Why I am doing so? Because what happens? This CH bond will be broken and there will be CC bond. There will be a CC bond, CH bond will be broken, and this carbonyl oxygen double bond that will also be broken, and instead now there will be single bond. And this hydrogen which is attached to carbon in acetone, now it will be attached to oxygen. And that form we are calling enol form. There is equilibrium sign, but mostly it will remain, that is, though it may differ. In case of acetone, greater than 99.9%, it remains in this form. And we call this form as keto form. Why? Because keto group is present. And the second form we call enol. Now, where from this enol term is coming? Enol is basically combination of two terms, in plus all. Combining together, we are getting enol. But why in and all? That is because you have CC double bond, which is for in. You have OH, that is for all. So in the same molecule you have all, you have in, we are calling it enol. And this exists lesser than 0.1%. Now we will go to phenol and enol. That is enol form of this. Basically here the phenol molecule itself is the enol. You know what is phenol, that we have seen in nomenclature of aromatic compounds. So this molecule is actually, we call it phenol. But see, as if it is the enol form, because this CC double bond is as if the in and this is the all. Now if I am breaking this OH bond, basically I am doing the reverse. In the previous example, you are starting with the keto form. And now you are starting from the enol form. That is the only difference. Why I am starting from enol form? Because that is greater than 99.9%. So if I am breaking this OH, now in this position there will be a double bond. And this CC bond, double bond will be removed. So see, in this position now you no longer having any CC double bond, but you have C double bond. Now if you are thinking why enol form is here greater than 99.9%, the actual reason is here aromaticity is lost when phenol molecule is converted to the keto form, and details of aromaticity that will be discussed later, not now. And in case of keto form, this C double bond, though this bond strength is very high, so that is it is more stable compared to the enol form. So see this keto form, enol form, one more example you can see here. So this molecule is basically, if I am writing the IUPAC nomenclature, it is 2-butanone, okay, or but-2-one. So here, as if this hydrogen is, we have removed, there is CC double bond, and this CO double bond is broken, and this position there will be OH. So this is keto form, this is enol form, but it is not only restricted to this type of compounds. You can also find it. Look at the other three examples. Here, instead of oxygen, we have nitrogen. Nitrogen carbon double bond, and we have OH. This type of group, it is called oxime. Fine. Now this OH bond, if I am breaking, now I have to make a NO double bond, and this NC double bond is now broken. So this hydrogen, now its position is here. So this is nitrosoform, different structure, different name. Now come to the third example. This is amine form because NH2 group is present. But suppose if I am drawing these two hydrogen like this and breaking this NH bond, this position now you will have CN double bond, and this CN double bond will be removed, and this hydrogen which is removed from nitrogen, now it will be attached to this nitrogen. See, so this is amine form, this is imine. Imine basically C double bond N, and there is hydrogen on any other group. Whenever you have this type of group, that is known as imine. The next example is, why I am discussing so many examples, because suppose the last example is given in the question and it is asked what type of isomerism is there. So you have to recognize that this is example of tautomerism, a type of structural isomerism. Okay, so that is why we are discussing all the varieties of tautomerism possible. Ketoenol is the most common. Then oxime nitroso, aminimine, and then the fourth one you are seeing here, lactam and lactine. Now lactam is a molecule where amide group is present in the cyclic structure. Amide group is, we know, CONH2. Now if CONH2, it is open, that is this side it is open and it is attached towards this side. But if I am removing one hydrogen here, so that means both sides now we need some attachment to satisfy the valence. So this CONH2 group, now it is a part of ring. And whenever you have this type of group as a part of ring, this is lactam. Here it is lactam, but this hydrogen, I am writing this hydrogen like this extended form because I will break it. And this position there will be formation of carbon nitrogen bond, and this double bond will be removed. This hydrogen now it will be attached to this oxygen. And now you can see some aromatic type of ring is formed. Once it is formed, though here nitrogen is present instead of carbon, now the name is changed. It is lactine. So these are the examples, and all these examples, basically hydrogen is the atom which is changing its position. So in keto form, the hydrogen is attached to carbon, then it is attached to oxygen. Here this hydrogen is attached to oxygen, now it is attached to carbon hydrogen. In the aminimine case, NH hydrogen is attached to N, but now it is attached to another N which is part of the ring. Okay, but in all cases it is hydrogen which is changing its relative position. Okay, and the last type, F, that means sixth type of structural isomers. Though it is not very common, but still we should know. As the name suggests, ring and chain, that means molecular formula will be same, but it can have cyclic structure or it can have open structure. So they will differ in terms of bonding of carbon atoms to form either open structure or cyclic or ring structure. Fine. Now alkenes are isomeric with alkanes. What it means? For alkene, we know the general formula we use CnH2n. Now for alkanes, when it is open chain, the formula is CN2n, CnH2n plus 2. But when it is ring, but still alkane, no unsaturation, then formula again becomes same as alkene. If you want to see example, suppose I am drawing a 3 card. This is alkane obviously because you do not have any double bond. Now here it is C, but total number of hydrogen is C3H6. So C, it is double. Now keeping the carbon same, if I am having a open structure, but I have to place a double bond now. This is also C3H6, isn't it? 2 hydrogen here, 3 hydrogen here, 1 here. So keeping carbon number same, if you are drawing a cycloalkane and if you are drawing alkene, they will be treated as ring chain isomer. So see here we have taken 1 butene, keeping carbon number same, so it is C4H8. This is also C4H8, but this is alkane, butane, without any double bond. You can also have 3 membered ring, but as you have to satisfy total number of carbon, so this methyl is now treated as substituent. So here cyclobutane is the ring chain isomer of 1-butene. Cyclobutane and cyclopropane cannot be ring chain because both are ring. And this third structure is also ring chain isomer of 1-butene. Okay. Now, just like alkene and cycloalkanes, they are isomeric to each other because they are having same formula. Same thing you can also see for alkynes. Alkynes and alkadiene. What is alkadiene? Alkadiene means same molecule will have two ene, diene. They are isomeric with cycloalkene. Now, just like alkene is same as cycloalkane, alkynes are also same as cycloalkene. Now, example is, suppose I am having HC triple bond C. What is the formula here? C4 H6, right? Now, keeping the carbon same, suppose now I am drawing a ring. It is C4H8, but if you place a double bond, then only it becomes H6. 2 hydrogen, 2 hydrogen, 1 hydrogen, 1 hydrogen. So see, this is cycloalkene. Cycloalkene. And this is alkyne. Now, keeping carbon number same, I can also have this structure, which is also C4H6, but this is alkadiene. Okay, 2 double bond. Now, one example we'll see. We'll end this at this slide just after seeing this. So, write all the ring chain isomer of pent-1-ene. Pent-1-ene we know its structure. So, pent-1-ene is basically, okay, let me draw it first. Pent-1-ene. Now it will be having ring chain isomer. Now the ring structure will be some cycloalkane. So now you can see all this. This is also this is C5H10. Remember C5H10, I have used this formula for showing chain isomer example. Again the same thing, but now we are using the same formula for ring chain, showing ring chain isomer. This is also C5H10. Now, when you are changing from 5-membered ring to 4-membered, there will be one methyl substituent. So this is 4-membered. Under 5-membered, one possibility. Under 4-membered, one possibility. Under 3-membered, now you can have 3 possibilities. So when it is 3-membered, rest of the 2 carbon, you have to that is, you have to satisfy it as substituent. Now both the carbon in the same substituent. Here we have 2 methyl. Their position at the same carbon. This is also 2 methyl, but positions are different, 1 and 2 carbon. And here also 1 carbon, but it is ethyl substituent. So these are the possibilities. If you consider the ring isomers, total 5 structures are possible. 1, 1, 3. Okay. And what about 1,3-butadiene? When you have 1,3-butadiene, it is basically this molecule. 1, 2, 3, 4. So see, at position 1 and position 3, double bond is there. So that is why the name is 1,3-butadiene. But for parent chain, total 4. Now if I draw its ring chain isomers, obviously I will start with this type of structure, but there will be a double bond, right? So this is C4H6. This is also C4H6. Now if I'm thinking, why not 3-membered ring? Now for 3-membered ring, you have to place a methyl group. Whether you place it here, you can also place it here. So here it is C4, 1, 2, 3, 4, 5, 6. So this is also C4H6. Here 1 hydrogen, 3 hydrogen, 1, 1. This is also C4H6. So these are the 3 possibilities for 1,3-butadiene. It's ring chain isomer. But for 1,3-butadiene, this is also isomer. 1, 2, 3, 4. But this is open structure. So you cannot say that this molecule, which is basically 1-butyl, this molecule is not ring chain isomer of 1,3-butadiene. because the functional group itself is different. Here we have two double bond. Here we have one triple bond. So we cannot say this is ring chain isomer. And how it can be ring chain isomer? Because we do not have any ring. These three are actually ring chain isomer of 1,3-butadiene. Okay. So by solving this example, now it is clear what it means actually. Now all the structural, we can discuss one problem because we still have some time. Here the question is saying that pentan 2-one and 3-methyl-butan 2-one, these two, what is the relationship between these two? Now we will draw this. Pentan 2-one is this molecule where at 2 position you will have double bond O. 3-methyl-butan 2-one, that means but. So total 4 carbon. 1, 2, 3, 4. 2 position 1, 3 position methyl group. Okay, this is substituent 2, 3 methyl. Now what is the relationship between these two? Is it functional isomer? See, functional group is same. In both cases it is CO. So you cannot say it is functional isomer. Then we have, is it chain isomer? Now that is a possibility because in the first case 5 carbon chain, but here it is 4 carbon chain because methyl is substituent. Is it position isomer? Now position isomer means here carbonyl position you have to see, but carbonyl, sorry, it is chain actually, but why it is not positional isomer? Because CO is, its position is not changed, but main chain there is some difference. Okay, so that is why it is not positional isomers, and obviously it is not stereoisomer because stereoisomer bonding connectivity remains same, only the spatial arrangement is different. Though we have not discussed it still, but it is not stereoisomer. Okay, so these will be under the category of chain isomer. That is the relationship between these two. A functional isomer of 1-butene. So 1-butene is basically CH, C, CH2, CH3. This is 1-butene. One position triple bond. Now functional isomer of 1-butene, which molecule? Is it the 2-butene? Now what is 2-butene? 2-butene is basically this molecule. But both cases, functional group we have not changed. So how it can be functional? This is not correct. Then 1-butene. 1-butene is this molecule. But here molecular formula is not same. Here it is triple bond, here it is double bond. See, it is C4. Basically it is C4H8. But here it is C4. Sorry, whether both are actually same. C4H6. So C4H8, C4H6 formula is not same. So how it can be? 2-butene. That will also be not same because for 2-butene also again it is C4H8. But the last one is possibility because 1,3-butadiene. Remember we have just in the previous slide we have just seen that 1,3-butadiene and 1-butene. They are not ring chain isomer obviously, but they are related to each other as functional isomer because here the group itself is different. But formula C, this is also C4H6. Total number of hydrogen. So this is also C4H6, this is also C4H6. But here we have triple bond, here we have two double bonds. So 1,3-butadiene should be the correct option. So we will end the session here. Next day, after discussing one or two problems, we'll start stereoisomer. Okay. Thank you for listening. We are ending the session here.